Hello everyone, welcome to my YouTube channel. In this video, I'll be explaining about how do you identify the position of the peaks in the NMR spectrum, and also what are the different factors which affect the position of the peaks in the NMR spectrum of any molecule. In my previous video, I had explained what is meant by NMR spectroscopy and also the principle that is involved in the NMR spectroscopy, and I have also explained how do you identify the number of equivalent and non-equivalent protons in the given molecule and how the number of these protons will affect the number of signals in the NMR spectrum of these molecules. If you have not watched the first part of the video, you can watch it now, and I have provided the link for the same in the description box. So now, in this video, I will be explaining about the factors which affect the position of the peaks. So before that, let me explain what is meant by shielding and deshielding of protons in the NMR spectroscopy. So since we are mainly dealing with hydrogen, that is proton spectroscopy, that is H1 spectroscopy, so I'll be explaining mainly about how the nuclei, the hydrogen nuclei, will be affected by the different electronic environment around it. So first of all, you can just imagine this hydrogen nucleus which is surrounded by a particular number of electrons. So now, these electrons which are surrounding the hydrogen, you can just imagine them as a shield of electrons around the hydrogen. So now, if there is a shield around hydrogen, so you just imagine when the magnetic field is applied to these nuclei, then because of the electronic shield, the effect of the magnetic field on the hydrogen nuclei will be comparatively low. So this effect is called as shielding of the hydrogen nuclei because of the surrounding nuclei, and hence the effect of magnetic field experienced by this nuclei is less, and hence the signals will be found in the lower regions. You can see this is the scale, and here this is marked from 0 to 10. So if there is shielding of the hydrogen nuclei, so what happens is the effect of magnetic field experienced by this nuclei is less, and hence the signals will be found in the lower regions. So this lower region is referred to as the upfield region. Again, these lower region and the higher regions, that is the numbers with respect to the numbers, this is specifically called as chemical shift. About this I will be explaining a bit later. So now, this is meant by shielding. What is the reverse of this shielding? You just imagine, suppose if there is a electronegative atom that is connected to this hydrogen. So now what happens? When an electronegative atom is connected to the proton, then electronegativity is nothing but the ability of an atom to pull the shared pair of electrons towards itself. So if the electronegative atom is connected to the proton, it will pull the shared pair of electrons towards itself, and because of this, the overall electron density around hydrogen will be comparatively less. So we can say that the overall shield that is present around hydrogen is decreased, or this effect is opposite of shielding, and hence we call it as deshielding. In this case, we call as the hydrogen is deshielded, or the proton is deshielded, because the electrons around this proton is pulled away from it by the neighboring electronegative atom. So whenever the number of electrons around this hydrogen is less, then what happens? We can easily say that the magnetic field will have more effect on the hydrogen, and hence the signals due to such type of hydrogens will be observed in the higher regions. The higher regions are named as downfield regions. So you can just remember D and D, that is, if the proton is deshielded, then the signals are observed in the downfield region. If the hydrogen is shielded, then the signals are obtained in the upfield region. So this is meant by what is meant by deshielding and shielding of protons due to the electrons around the protons. So next, coming on to the specific term, that is chemical shift. Now here, as I've already told, the higher regions and the lower regions, the numbers what we can see, that is 0 to 10, they have a specific naming, that is nothing but the chemical shift. It is expressed either as delta or tau. That is, you can either represent it in the form of delta or in the form of tau. They both are related to each other as delta plus tau is equal to 10. So now what is meant by chemical shift? Chemical shift is nothing but the difference in the absorption position of the proton, which is under study, with respect to TMS. So this TMS is nothing but the reference compound which we take in the NMR spectroscopy. So why do you need a reference? Okay, what are the reasons why we need to take this TMS? TMS is nothing but tetramethylsilane. So why do we need to take this TMS as the reference compound? Why do you need a reference compound in the NMR spectroscopy? I'll be explaining in the next slide. So now, whatever the difference you can see, here you can see in this picture, at 0, you can see here, at 0, you can see the signal due to TMS, and these are the signals due to the different protons. This is for ethanol, so CH3 will give one signal, CH2 will give a particular signal, and OH will give a separate signal. So here, with respect to TMS, what is the difference in the position? So for CH3, what is the difference between the TMS and the CH3 signal? This is the chemical shift for CH3 proton. Next, for CH2, same way. For all these protons, you have to just see what is the difference between the position of the peaks due to that proton and the position of the TMS signal. So TMS will always give a signal at 0. So now usually we measure this chemical shift in form of ppm or delta. So you can say that TMS will give a signal at 0 ppm. So you can just see in this picture. So OH peak you can see at around 5. So we can say that the chemical shift of OH is 5 ppm, that is the difference between the absorption position of OH and TMS is around 5. It's not exactly 5, maybe 4.8 or 4.9. So now there is a formula to calculate the chemical shift in terms of delta. So position of the signal, that is position of the signal of that particular proton, minus position of the TMS peak, that is it is at 0 ppm or 0 delta, divided by the operating frequency of the NMR spectrometer. So you have to calculate according to this formula and you will get the chemical shift value. So why do you take this TMS as the reference compound? What are the different reasons why we need to take this TMS as the reference compound in NMR spectroscopy? First of all, this tetramethylsilane or the TMS, it has 12 equivalent protons. So in my previous video I have explained how do you calculate the number of equivalent protons and how do you identify the number of equivalent protons in a given molecule. So here you can see all these protons are CH3, that is methyl protons, and all are connected to the same silicon atom. So all these protons are equivalent to each other. There are 12 such equivalent protons, and we know that whenever the protons are equivalent, they will give rise to one single signal. So now you can just imagine, whenever we take a reference compound, if the compound itself gives 3 or 4 signals, then it will be difficult for us. So if it is only giving a single signal, then it is more convenient because we can just ignore this reference signal and then we can observe whatever signals are required for the compound under study. So the second point is it will give only one strong signal because of the 12 equivalent protons. It is also chemically inert. Inert in the sense it does not react very easily with other compounds. So we can just imagine why this point is so necessary. Because if the reference compound reacts with other compounds or the compound which we are studying, then it may lead to some other product and the products will give some other signals. Then we may not be able to understand what are the signals that have to be obtained for the compound under study. So we need to select a reference compound in such a way that it should not react with the compound under study. It also has a low boiling point. That is, after the NMR spectrum has been recorded, you can easily remove off this TMS. That is, we do not require this reference compound after the NMR spectrum has been recorded. So you can easily remove this off by evaporation. So because of its low boiling point, you can separate this compound from the compound under study. It is also soluble in most of the organic solvents. So here we know that whenever we are recording the NMR spectrum, we usually use the different solvents. That is, we dissolve the compound under study in different solvents like chloroform, deuterated DMSO and so on. So what happens is, even the reference compound has to be soluble in the same solvent so that we can record the NMR spectrum. So here this TMS is soluble in most of the organic solvents. So because of this, again, this adds to the benefit of using this TMS as the reference compound. The next point is electronegativity of silicon is low. So we know that whenever the electronegativity is high, then the particular element, the electronegative atom, will pull the electrons towards itself. But here the silicon has low electronegativity. So if electronegativity is low, then what happens? All the protons which are there, they will have the required shielded electrons around themselves. So if it is shielded, then obviously the signals will be obtained in the upfield region. So here all the protons are equivalent and they are shielded because silicon is having very less electronegativity. So because of the shielding, the signal of TMS is obtained in the highly upfield region. So because of that, you can see the position of TMS signal is at 0 ppm. So next, coming on to the factors which affect the chemical shift of a particular compound. So chemical shift is nothing but the position of the peaks in the NMR spectrum. So there are three different factors which affect the position of the peaks in the NMR spectrum. So first one is electronegativity of the adjacent atom. This I have already explained. So this I will be explaining by giving some examples. The type of hybridization of the adjacent atoms, whether it is sp3, sp2 or sp hybridization, and also the effect of magnetic induction. So because of the pi electrons in the particular compound, maybe it is in the presence of aromatic compound or alkenes, alkynes and substitutions of the same. So here there is one more effect, that is an isotropic effect because of the movement of the pi electrons. So first, coming on to the electronegativity of the adjacent atoms of the proton. So before that, you can just see a particular spectrum, the NMR spectrum. So you can see here for this molecule, this is one type of proton, that is CH3 proton. Again we have, this is one more type, CH2. Here we have one more type of CH2, one more type of CH2 proton, and then we have the protons of the aromatic ring. So based on that, you can see there are different signals that are obtained here. So there are 5 different signals that are obtained along with the splitting. So what does splitting mean and how the splitting will occur, I'll explain later. So based on the number of different types of equivalent protons, you can see the corresponding number of peaks in the NMR spectrum. So first, coming on to the first factor, that is electronegativity of the adjacent atom. So this I have already explained how it affects the position of the peaks in the NMR spectrum. So first of all, the hydrogen or the proton will be surrounded by a particular number of electrons. If an electronegative atom is near to this hydrogen, then the electronegative atom will pull the electrons towards itself. So this hydrogen will be deshielded, that is, the number of electrons around it will be lesser, and hence because of this deshielding, the signal that is due to this particular hydrogen will be obtained in the downfield region. So this is a simple example here. So for CH4, next here, by including one electronegative atom, that is chlorine, so this will give CH3Cl, chloromethane. Then we have the CH2Cl2, dichloromethane, and then we have CHCl3, trichloromethane. So here you can see, by the presence of one electronegative atom which is nearing the hydrogen, so here there is no electronegative atom at all, so you can see the position of the peak is at 0.23 ppm. Now here in CH3Cl, you can just imagine, so CH3 Cl. So you can see there is Cl which is present here. So Cl is an electronegative atom. It will try to pull the electrons towards itself. So overall we can say these protons, the electrons around these protons will be, the electron density will be decreased, and hence these protons will be deshielded when compared to the methane. So because of the deshielding, the signal will be obtained at a downfield region when compared to the CH4, that is, when compared to 0.23, this will be in the downfield region of 3.1. Next we are speaking about CH2Cl2, where there are two chlorine atoms. Again, the electronegative effect will be still higher because there are two chlorine atoms. Again, they'll try to pull the electrons towards themselves. So because of this, the hydrogens will be more deshielded. The electrons around hydrogen will be more deshielded, and hence the signal will be found at a highly downfield region when compared to the chloromethane, and it will be at 5.3 ppm. So if there are three chlorine atoms, the deshielding will be still higher and the signal will be obtained at a still downfield region, that is 7.3 ppm. So you can see this, the NMR spectrum of these particular molecules. For CH4, you can see this is the peak. For CH3Cl, this is the peak. Next, for CH2Cl2, this is the peak at 5.3 ppm. For CHCl3, this is the peak at 7.3 ppm. So we can say, as the number of electronegative atoms increases, the signal will be slowly shifted towards the downfield region. So even this is one more example. Here, iodine, bromine, chlorine and fluorine. We know that fluorine is highly electronegative when compared to chlorine, bromine and iodine. So here the signal due to this compound, where one of the hydrogen in methane is replaced by a halogen. So when it is replaced by fluorine, which is having a very high electronegativity, the signal will be found in the downfield region of 4.3 ppm. When it is substituted with chlorine, we have the signal at 3.1 ppm, and here we have for bromine, it is at 2.7, and iodine, which has a very low electronegativity, so the signal will be not in a downfield region, it will be in the upfield region, so 2.2. So we can just say that as the electronegativity of the particular atom increases, or as the number of electronegative atoms increases, the signal will be found in the downfield region. So next is, you can just, this is just a gist of whatever I have told. So as the electronegativity increases, this will result in deshielding of the protons, that is, the electron density around protons will be decreasing, and this will result in the increase in the chemical shift. That is, the signals will be found in the downfield region. Next is effect of hybridization. As I've already told, there are three different factors which affect the chemical shift. One is the electronegativity of the adjacent atoms, then it is hybridization of the adjacent atom, and then the anisotropic effect. So here we have to just remember, in hybridization of the adjacent atom, as the S character. So whenever we are speaking about the neighboring atom, we have to see what is the hybridization of the neighboring atom. Then we have to see in the hybridization in sp3, sp2 or sp, what is the percentage of the S character in that particular hybrid orbital. So if the S character is more, that is S character of the neighboring atom to that proton is more, then the proton will get deshielded and hence the signal will be in the downfield region, or this will lead to higher chemical shift values. So now first coming on to sp3, here we know that the percentage of S character is 25. So how do we calculate it is, the total number of orbitals is 4 because S and p3, so total are 4. Out of 4, one orbital is S. So what is the percentage? That is 1 into 100 divided by 4. So this will give you 25% of S character. So we know that whenever there is sp3 hybridization, there will be single bond, and usually these are alkyl substituents. So what happens here is, it is when the proton is attached to the alkyl groups, so the delta, that is the chemical shift value, is found to be 0.8 to 1.7. Next, sp2 hybridization. In this, the percentage of S character, how do you calculate it? Total number of orbitals, one is S and 2 p orbitals. So total number of orbitals are 3. Out of 3, 1 is S orbital. So what is the percentage? So 1 into 100 divided by 3. So that will give you the percentage of S character as 33.3%. So if you compare sp3 and sp2, in case of sp2, the percentage of S character is higher. So here we know that the bond type, whenever there is sp2 hybridization, it is a double bond, or we can say there may be alkene group. So vinyl protons, so here they will have a higher chemical shift value of 4.6 to 5.7 delta. That is nothing but ppm. You can just express it in any ways. So now we can see as the S character increases. So here from 25, it is increasing to 33.3. So proton is getting deshielded and hence the chemical shift value is increasing. You can see here it is 0.8 to 1.7. Here the chemical shift has been increased to 4.6 to 5.7. Next, coming on to sp hybridization. So again, percentage of S character. So total number of orbitals are 2. So out of 2, 1 is S. So out of 100 it is how much? It will give you 50%. So whenever there is sp hybridization, we know that it is the acetylenic group. So acetylenic proton, they will have a chemical shift of 2 to 3. But now there is a discrepancy, because here from sp3 to sp2, since there is increase in the percentage of S character, there is increase in the chemical shift. But here you can see from sp2 to sp, again there is increase in the percentage of S character, but the chemical shift value has been decreased. So this reason why there is decrease in the chemical shift value from sp2 to sp, this is mainly attributed to the next factor, that is the effect of the anisotropic effect. Okay, so what is this anisotropic effect? Which is the effect due to the pi electrons, that is circulating pi electrons. So how they will affect the chemical shift. So now coming on to the third factor which affects the chemical shift or the position of the peaks in the NMR spectrum. So that is called as anisotropic effect. So this is mainly due to the circulation of the pi electrons especially in alkenes, alkynes and aromatic compounds. So let me just show it in the form of a picture which will make it more clear to you all. So here, in case of alkenes, we have to just concentrate on the protons since we are studying about proton NMR spectroscopy. So this is the direction of the external magnetic field and this is the direction of the circulation of the pi electrons. So you just need to see the direction of the circulation of the pi electrons near the protons. So you can see here, this is the direction upwards. Even the direction of the external magnetic field is upwards. When both the directions are in the same, that is both the direction of the circulation of the pi electrons near the proton and also the direction of the magnetic field, external magnetic field is also in the same direction, then we say that the effect adds up, or we say that the proton is deshielded and the chemical shift increases. So in case of alkenes, both are in the same direction and hence the proton is deshielded. Whereas in case of alkynes, just we need to concentrate the protons. Okay, so here we can just observe, here you can just see this is the direction of the external magnetic field which is upwards, and here you can just see this hydrogen. Near the hydrogen, what is the direction of the circulation of the pi electrons? So this direction is downwards. You can see the arrow, this is in the downwards. So both the directions are opposite to each other, that is direction of the external magnetic field and the direction of the circulation of the pi electrons near the proton, in the vicinity of the protons. It is in the opposite directions and hence we say that in case of this alkynes, that is acetylenic protons, the protons are shielded, and because of this what happens is the chemical shift value decreases. So you can see here, so because of the anisotropic effect, the two directions are opposite to each other and hence the chemical shift value of the sp, that is whenever the adjacent atom is connected to the adjacent atom is sp hybridized, then the proton which is connected to the sp hybrid atom will have a lower chemical shift. So this is about alkene and alkyne. So because of this, the alkyne chemical shift is lower than that of alkene, although the percentage of S character is higher. So this is for the aromatic system. So again we need to see the hydrogens. So here this is the direction of the external magnetic field and here you can see the arrow. This is also pointing upwards, which is near to the hydrogens. So we can see both are in the same direction. So even in case of aromatic system, the protons are said to be deshielded and hence this chemical shift value is higher. Next, coming on to, you have seen in the previous, in the spectrum, when I have shown the certain NMR spectrum, you have seen that there are some splittings in the peaks. So what is the splitting? Why the splitting occurs and what is it called as? This splitting is called as spin-spin splitting. So whenever there are different types of hydrogens, we know that in a particular molecule there may be 3 different types of hydrogens, 4 different types of protons, etc. So when these different types of protons, different types of non-equivalent protons, when they interact with each other, this will result in splitting of the signals. So this interaction between the different nuclei is called as spin-spin coupling. So because of the coupling, there is splitting of the signals. This coupling is mainly involved due to the intervening bonds, that is bonds between these different types of protons, that is the different groups which involves the different types of protons, and the effect also is more when the protons are near to each other. So now how the splitting will take place? So with this NMR spectroscopy, we can identify how many number of hydrogens are present to the particular hydrogen which we are studying. And based on this, we can say that a particular signal will be split into n plus 1 number of peaks. Suppose if the neighboring hydrogens are 2, then the particular signal will split into 2 plus 1 peaks, that is 3 peaks. Suppose if the neighboring hydrogen is 3, then the particular signal will split into 3 plus 1, that is 4 peaks. If there is no neighboring hydrogen at all, then there is no splitting. So in that case, the signal will be in the form of a singlet. Singlet in the sense there will be no splitting, it will be a single peak. So now how do we identify and how do we name this different splitted peaks? Suppose if the number of neighboring hydrogen is 0, then this will result in a single peak. We call it as singlet. And the ratio, that is, since it is only one peak, that there is nothing called as ratio here. It is only 1. The intensity is 1. Now, suppose if there is one neighboring hydrogen, then according to n plus 1 rule, it will split into 2 signals, that is 1 plus 1. So we call such type of signal as doublet. That is, a single signal will split into 2. And the ratio of these 2 signals is 1:1. That is, the splitting will be like this. One single peak will split into 2 peaks. Suppose if the number of adjacent hydrogens are 2, then according to n plus 1, it will give rise to 3. It will split into 3 and the ratio is 1:2:1. Now how to remember this value? Take first number 1, add these two numbers 2 and the last number 1. So we get the splitting like this, 1:2:1. Next, if the number of adjacent hydrogens is 3, then it will split into 4 signals, that is called as quartet, and the intensity is 1:3:3:1. That is, first number keep it as such, second number 1 plus 2, that is 3, again 2 plus 1, 3, and the last number keep it as such. Next, if the number of neighboring hydrogens are 4, then this will split into 5 signals, that is called as quintet, and the ratio is 1:4:6:4:1. So again 1 keep it as such, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and the first and the last numbers keep it as such. So next is coupling constant. So whenever there is splitting of the signals, that is the distance between the splitted signals, this is always a constant. Now here you can see this is 15 Hertz, here also there is 15 Hertz, here also there is 15 Hertz, and this is called as the coupling constant. For a particular signal which is split into different, maybe doublet, triplet or whatever it is, the distance between the splitted peaks will be a constant. So that is called as coupling constant, called as J, and it is expressed in terms of Hertz. So now coming on to a few examples, how do we identify the number of peaks for particular compounds? So first, taking this example, here we have one hydrogen and here we have already 3 bonds, so one hydrogen here. So since there are 2 hydrogens, I have named these 2 hydrogens as A and B. Now here we can see for hydrogen A, there is one neighboring hydrogen. So the signal due to A will be splitting into 2, that is n plus 1 will be 1 plus 1, that is 2. Here for hydrogen B, there is one neighboring hydrogen because of the carbonyl group. So here again the hydrogen due to B will split into 2 because there is only one hydrogen, so 1 plus 1 will give you 2, doublet. So because of that, both hydrogen A and B will give doublets each. So here we can see the number of protons, the types of protons are 2. So A will give a doublet and B also will give a doublet, and the peak area ratio, that is Since both are doublets, the ratio is 1:1 and 1:1. Now the question is, which one will be downfield and which one will be upfield? Whenever we have this carbonyl group, the hydrogen which is connected to the carbonyl group, it will always be highly deshielded, because the carbonyl oxygen will pull the electrons towards itself. So because of this, it will be highly deshielded. So whenever the hydrogen is connected to the carbonyl group, it will be in the downfield region. So here we have the two signals in the NMR spectrum, that is two doublets. So this is due to the carbonyl HA and this is due to HB. Next example, here we have, here already 3 bonds are there, so 1 hydrogen. Here only 2 bonds are there, so there should be 2 hydrogens. Now this hydrogen, I have named it as A. These 2 hydrogens, these 2 are equivalent, so I have named it as B. Now for A, there are 2 neighboring hydrogens. So according to n+1 rule, it will split into 3. So this will give a triplet, whereas hydrogen B, it has only 1 neighboring hydrogen. So according to n+1 rule, 1 plus 1, it will give a doublet. So hydrogen B will give a doublet, hydrogen A will give a triplet. Now which will be downfield and which one will be upfield? Hydrogen A has 2 neighboring electronegative chlorine atoms. So this will be in the downfield region, and hydrogen B has only 1 chlorine atom which is neighboring to it. So it will be in the upfield region. So you can see here the types of protons are 2. For A, as I have already told, there are 2 neighboring atoms, so this will give triplet. For B, there is only 1 neighboring atom, so it will give a doublet. So peak area ratio will be 1:2:1 for triplet. For doublet, it is 1:1. Now we know that since A has 2 chlorine atoms attached to it, so it will be in the downfield region, whereas B has only 1 chlorine atom, so it will be in the upfield region. So you can see here, for B, it is a doublet in the upfield region. For A, it is in the downfield region and it is having a triplet. Next example, so here again, here there are 3 hydrogens, here there are 2 hydrogens and a chlorine. So A, I have named for these 3 hydrogens which are equivalent, and B, I have named for these 2 hydrogens which are equivalent. So A has 2 neighboring hydrogens, so this will give a triplet. B has 3 neighboring hydrogens, so it will give a quartet. B has a chlorine atom which is adjacent to it, so this will be downfield, whereas A will be in the upfield region. So type of protons are 2. For A has 2 neighboring protons, so it will give a triplet. B has 3 neighboring protons, so it will give a quartet. And B has a chlorine which is attached to it, so it is downfield, whereas A does not have any electronegative atom to it, so this will give the signal in the upfield region. Peak area ratio for triplet 1:2:1, and for quartet it is 1:3:3:1. So this is the this is the NMR spectrum for this molecule. So you can see here triplet is found in the upfield region and the quartet is found in the downfield region. Next, last example is for ethanol. So here we have 3 different types of protons. One is this hydrogen of the OH group. Next, CH2 group will have, this is one type of hydrogen, and the 3 hydrogens of the methyl group will form one more type of hydrogen. Now we have the signals. The type of protons are 3 here. For A, there is no neighboring hydrogens. So what happens is this will be formed as a singlet. For B, there are 3 neighboring hydrogens. So it will give a quartet. Next, for C, there are 2 neighboring hydrogens. So this will give rise to a triplet. So now A is directly, the hydrogen A is directly attached to highly electronegative oxygen. So this will be in the highly downfield region. Next, B is having oxygen at a particular vicinity when compared to C. So B will give the signal in the downfield region and C will give the signal in the upfield region. But B will be in between the signals of A and C. So again we can see the peak area ratios. For singlet it is 1. For quartet 1:3:3:1. For triplet 1:2:1. So we have here, this is for OH group, that is A, and then we have for B, we have the quartet, and then we have for C, that is the triplet. So this is found for C, which is in the upfield region, and this is for B, which is in the downfield region, and this is for A, which is in the highly downfield region because of the oxygen which is directly attached to hydrogen. So this is how we identify the peaks for the particular molecule. We need to identify the number of equivalent protons in the given molecule, and then we have to see how the splitting will take place, and then we have to decide based on the number of electronegative atoms whether the signal will be found in the upfield or the downfield region. I hope this video makes it clear how to identify the different peaks and the position of the peaks in the NMR spectrum, and also about the principles and the shielding and deshielding that is taking place for the different protons. I hope this video is helpful for you. Thank you for watching the video.